So we are at almost the end of the introductory cosmology unit, and today we are just going to look into the qualitative idea of the baryon antibaryon asymmetry. By this we basically mean that the number of baryons are more compared to antibaryon, and in fact antibaryons are something which is like more of antimatter, and the universe that we see around us is more or less composed of matter and not antimatter. So what is the reason behind that? What are the theories? Before we start, we have to just consider this thumb rule that we really don't know which theory is correct. There are very less experimental evidences to prove anything as such. So the fundamental question remains whether the universe is made up of matter and not antimatter. Okay, and universe whatever is obviously made up of matter, because whatever we see around us is made up of matter. We are not really detecting anything which is made up of antimatter. So that's the fundamental question. So what happened was, after the Big Bang, the universe was extremely hot, and we had the Big Bang. Okay, we've discussed a number of times, and there was a lot of energy for making the particles and antiparticle in pair. So there, at the beginning, there might have been generation of particle as well as antiparticle, but there is something which is called annihilation, which we know, and it may be said that as the universe cooled, these particles and antiparticles annihilated in pairs. Now, if it annihilates, basically there is the particles and the antiparticles won't be there. So the large amount, amount of matter and antimatter would have been equal. Okay, if it was equal as such, everything would have annihilated and the universe would be empty. So if there is no particle or antiparticle, the universe can be considered empty to be its true sense. Please keep this in mind, that the universe is not empty. Even the space has got some kind of energy. So there is no such thing as vacuum in its true sense if we go for this Big Bang theory and so on. Okay. So when the universe was hot, there must have been more matter than antimatter, so that after it cooled, we and the stars were left over. So it was not that at the beginning of the universe matter and antimatter was same in number. They must have been lesser in number. Okay, the antimatter would have been less, the matter would have been much more, because of which we will actually see that whatever existed around us was mostly matter. Okay. But it could be result of, but there can be another theory that it could have been the result of the laws of nature which we can discover. So that means some of the things which is not yet discovered, some laws which might still be there to be discovered. I think once I have already discussed it in the class, that if you consider tossing coins, and if you, let's say, consider tossing 50 coins, you will see that there might be some kind of biasness, let's say around 30 heads and 20 tails. Okay, but as you keep on increasing the sample space, let's say you say 1000 coins, okay, you will see that the number of heads and the number of tails will come closer and closer, and probably it will be a 50-50 ratio. So might be 500 head and 500 tail. Now this is what happens naturally. Now suppose I apply some kind of field. Let's say I toss the coin and I am putting some magnet in the coin, and I have got a magnetic field, so that the coin will turn in the face in which I want. Let's say it will turn only in head. Okay, why is that happening? Because I'm using an external force, let's say a magnetic force, so that it might happen that if I toss 1000 coins, all 1000 coins will be basically head. So what happens is, there is obviously biasness, but that biasness happened because I used an external energy, external force. So it might happen that when the Big Bang actually happened, there might have been another external force or something from the nature, okay, which we are still not aware of, because of which actually there was more matter and not antimatter. So this is in fact a theory which is actually also given. Okay. So what happened was, when the universe actually started and the Big Bang actually happened, and within the first 10 to the power minus 10 second, the temperature was approximately 10 to the power 15 Kelvin, very high. Okay, and at that time the electroweak interaction was more or less active. Okay, we are going to look into these interactions also later in another unit. Okay, and then as time passed, let's say in the 10 to the power minus 6 seconds, okay, the temperature dropped to 10 to the power 13 Kelvin, and then there was baryon pair annihilation. okay, and then the annihilation process started. But as we know that the matter baryon or antibaryon were not same or equal in equal in number, so the annihilation did not empty the space, okay, there were still baryons which were left over, and that is the reason that at the first minute, okay, the temperature dropped to 10 to the power 9 Kelvin and nucleosynthesis happened, okay. So when the temperature dropped, the nucleosynthesis happened. So what happened was the temperature was cooler, the universe was cooler, but temperature was high enough for nucleosynthesis to happen. And then from the beginning of time, some 3 lakh years passed, okay, and then the temperature dropped to 4000 Kelvin. So everything was coming in range, and then recombination happened, and then we actually had larger atoms and molecules and so on, okay. And then came 1 billion years. So 1 billion years, the average temperature of the universe dropped to 20 Kelvin, and that was good enough for forming galaxies, okay. And once the galaxies formed, that means our existence was also coming into picture. And when it came for 15 billion years, means that today's average temperature of the universe is 3 Kelvin, okay, and then at this temperature we are basically existing today. Now this temperature is a temperature of the universe. Please consider this. If we consider the temperature of the earth and consider an average temperature of let's say 40 degree or 50 degrees Celsius, this is only 3 Kelvin, okay, it's in the negative range, okay, because we are considering the average temperature of the entire universe, okay. So this is what is existing today. So this is basically the timeline that we have, and the population of the more general class of the particles called the baryons does not change. So if we consider the average of proton and neutron throughout the universe, it will remain fixed, or it usually remains fixed, okay. But then baryons and antibaryons can be created and annihilated in pairs, but the excess of baryon over antibaryon, known as baryon number, is constant. So something which is baryon number, I think you came before through this, okay, used this term when we talked about conservation laws and all, okay. So the excess of baryon over antibaryon is something which is also referred to as the baryon number. So if we consider any reaction where baryons are involved, right, we usually consider that the baryon number is actually conserved, okay. A similar thing is also there for leptons, okay. If we consider something like leptons, we have the lepton number, that means for neutrino, okay. So what happened was, since the baryon number is conserved, so the number of baryons or the baryon number is constant as far as back into the history of the universe is concerned, okay. So we can consider that the baryon number is constant. Now since the lepton number we are saying is also a constant, and we are talking about neutrino, we already know, and it has been proved, that neutrinos are there, but it is very hard to detect. So in order to determine the lepton number, we basically have to count neutrinos. So we assume that the neutrino is conserved in a particular reaction, but in order to do it practically, it's an additional task, because we need to detect neutrino, and it is actually very hard to detect the same. So should we talk about baryons, or we should talk about quarks now? Now as science progressed, it was seen that baryon, like let's say proton and neutron, it was actually a composite of 3 more fundamental objects called quarks, okay. So we already know this from our high energy or particle physics knowledge, and each baryon will basically consist of 3 antiquarks. So we have got each antibaryon with 3 antiquarks, and the baryon will have 3 quarks. So all baryons are composed of 3 quarks. So if we say baryon number, okay, of the universe, it is basically 1/3 the quark number, because one baryon is composed of 3 quarks, okay. So one baryon is equal to 3 quarks, right. So one baryon is composed of 3 quarks. So we have to look into this picture. That means considering quarks, it's better to talk about quarks and not in terms of baryon. So the composite nature of baryon basically implies that the ultimate explanation of the matter antimatter asymmetry must be framed in the language of quarks. So we should talk more about quarks and not about baryons if we go into the more fundamental aspect, okay. So the matter excess of the universe is referred to as the baryon asymmetry. So if we talk about more of a baryon antibaryon asymmetry, we can talk specifically about baryon asymmetry, because baryon number is more compared to antibaryon. Okay, and the production of matter excess is called baryogenesis. So this is a technical term. Basically, if we have excess baryon, we basically put it under a theory which is baryogenesis. So Shakrov, the scientist, actually has given three conditions based on which we can say that there is an existence of baryon asymmetry, and he has given his theory in the year 1967. So the three conditions necessary for an explanation of the baryon asymmetry, it must be a process that changes the baryon number. Okay, so basically baryon antibaryon are not the same in number, so if it must be a process which actually have a excess of baryon, so the baryon number will exist. Such baryon number violating process have not yet been observed. So it is just a theory, experimental part is still to be done, and we still don't know whether it is true or not. Okay, the next one which we have already discussed, the laws of nature must be biased. Okay, so that additional force must be there, that matter excess results and not an antimatter excess. Okay, and finally the baryon number violating process must be out of thermal inequilibrium. So there was a temperature difference, there was a thermal inequilibrium in the system of the universe initially, because of which there was more baryon compared to antibaryon. Okay. So this was a brief overview, a very short and brief idea of baryon antibaryon asymmetry. Thank you.